Hello and welcome to Computer Vision Fundamentals. My name is Jorge and I'm excited to introduce you to the field of computer vision in the context of engineering. So I will be leading you through this workshop, and let's start by looking at the statistics first. Global computer vision market is expected to reach 5.8 billions by 2030. Other companies such Business Insights give a more optimistic prediction, uh, but we are talking about regardless like 170 billion, something like that. We see that the global trend is that computer vision market will grow over the next years. And if we look on the plot on the right side, we have that it shows. So for now, you see hardware is very dominant with 74% of market share. Also, you see that manufacturing accounts for a huge share of the piece. And then, as an engineer, I've seen firsthand how these systems are applied, and it is not only useful in the sense of engineering and manufacturing, but also in healthcare. It can be used security, and you probably can also use it. You probably have a smart camera already working for you in your home. So this is just to show you that computer vision has many applications. Some of them are still open to be explored, and to give you an idea that with the growth there is possibility also. What it means is there is opportunities to do real work in this area. Some of the things that can happen, for instance, is that computer vision will integrate more in our daily lives, and we have seen this actually. So we have also quality assurance and inspection. We have manufacturing, that is one of the big drivers of its use. We have retail experience. We have also learning as well. So there is a lot of sectors and different areas where you could, in theory, apply computer vision. One of the limitations with computer vision is that also could be expensive. Cameras are not cheap in general, but there is also with a good expertise you can select a proper camera that does the job but is not too expensive. So there are always trade-offs, and this is part of the engineering, let's say, decision and the business decision as well. So in general, you can see that computer vision is used in many areas, and you learning to use computer vision doesn't mean that you have to be a creator of this technology. You can be a user, an informed user about the technology, or you can have like an informed opinion, let's say, when it comes to this technology. So in this course, of course, we're gonna cover the fundamentals of computer vision, so you get a general idea of what is and what are the challenges and the kind of equipment and also software level that we can use. So let's start with a few challenges. And one of them is security. Like, you don't want your data to be at the mercy of anyone. There is also, when it comes to ethical and privacy concerns, which is close to the data security, but it's not the same. Because, for instance, it could be that you're secure, but you're not private. So, right. So then you have the application sometimes need to be the complexity of the integration. Is significant. Then there is computational resources. And in general, is with AI, we have gained some level of robustness to the systems, but systems tend to be fragile when it comes to very complex cases. So AI is helping for sure, but it's not the one in all solution when it comes to computer vision. We still have so many things to figure out. So here is one video of a self-driving car that crashed onto. Thankfully, it didn't crash directly on the train, but it was a significant accident, and you saw all the, it's using computer vision technology, the self-driving technology, and it's not perfect, and the different environmental conditions might fail, especially if you're only using cameras, which I think is the case for Tesla, then you might have problems of reliability in certain scenarios. So just to say that this is just an example, I'm not trying to hate on Tesla or any other brand. It's just an example to show you that the systems have points of failures. The systems are not necessarily perfect, and they tend not to work in all conditions. What you try to do is that to make sure to do a lot of testing to make sure that most of your conditions are covered, right? But something like that, for instance, it seems like the camera, the system just didn't work properly. So to conclude, I want to thank you for taking this course. This is free course available here in Udemy. This is just the starting of a larger workshop that I've developed that you can check my profile if you feel like it. And then this project, we are going to do a project. We're going to do something practical. We're going to do just software level, because also there's a limitation when it comes to the amount of time that I can devote without locking the course in terms of a paywall. But we're going to build an actual product. We're going to build an actual product, and this will be fun for sure. We're going to test. And the only thing that I ask for you is to have the motivation and the willingness to explore with me, to explore together the application. So thank you very much, and see you there. Hello, welcome to this first introduction to computer vision. And today we're going to start with a simple question. What is computer vision? So this is the first thing we have to define when we are dealing with this topic, and is to understand what is the goal, what is the objective of computer vision, why do we even use this kind of technology. So the first thing is the goal of computer vision is to make useful decisions about the physical world. So our objective is to capture the information that we have around us, the visual information, and with this information to take meaningful decisions. So that's our primary goal when we are talking with computer vision. So this process can be divided in a general perspective. I would say we have the real world, so we have this. Then we acquire images, right? After which we have information. And finally, we can take a decision. So each part of the process has a specific name. For instance, when we're moving from the physical world to the images, we are doing an acquisition. So we are doing an acquisition. Here we are processing information. So we're processing these images, we are acquiring the information, and finally we are doing an analysis to make a meaningful decision. So computer vision helps to support decision-making process. So of course there are systems that are autonomous, and that's the idea of most applications, is to allow the system to take the decision itself, whether something is good or not, or whether something has enough quality to pass or not. But from a general perspective, this is the goal of computer vision, and this is sort of the process that we have when it comes to computer vision. So at each part of the process, we have different technologies that support us on the whole process, right? I wanted to also add a keyword to computer vision: multidisciplinary. Computer vision is multidisciplinary, and many people sometimes think that computer vision is only related to somehow to computer scientists, but it is not true. It's very far from true, because we have a lot of engineers working with this field. So we have mechanical engineers, we have electrical engineers, we have electronics engineers, and like business managers working with these technologies. Maybe not at the root technical level, but for surely they have to understand at least how is the process, and let's say from a macro perspective, like what entails to bring something to the market. So this is for sure something business managers we talk about, also neuroscientists. Of course, we're talking software engineers as well. So we have many fields that are embedded with computer vision, and computer vision itself is something that, as I explained on the previous video, was that it's something that is growing, something that is evolving and changing. So if you look back 5 years ago, many things changed in computer vision, and we do things, maybe perhaps some things we do differently. And for instance, now with the growth of neural networks and AI, computer vision is changing a lot. So it's very dynamic field, that's for sure. And I want to also here quickly tell you, so the meaning, let me just quickly move this here, and then just tell you a little bit here. For instance, in acquisition, we use sensors to acquire different images, to acquire videos. So we use sensors. For instance, we have CMOS, we have charge coupled devices. So we have different technologies that allow us to acquire the information. So when we're talking processing, we can talk about maybe enhancing contrast. We're talking about maybe detection of certain edges or something for filter analysis. So here we process all these data that then we pass to the analysis, and we derive a meaningful decision. So it could be probably to say if a product has good quality, if there is I don't know, maybe it needs to detect face or other applications. So with that being said, I wanted just to give you an example of computer vision and how it's implemented, let's say. So imagine we have a box. So we have a box, and we are here, and we want to verify if this box, we're seeing this box from the, I don't know, let's say, let me just get this 3D going here. So we want to verify that there is a X logo on this box. So we can do it. We can totally just go up and see where is this located, and we can call it for today, right? Now imagine, so we say, okay, it's good. So it can go to our customer. But imagine if we have not just one, but we have many. So we have one that is coming here, then we have another one. And to make it more fun, just imagine that it is, this is carried on a belt. So this has a given speed. So we're talking that every given distance d, let's call it, it's never that perfect in the real world, but at a given distance we have the packaging common. So we need to verify here if we have the logo or not. We can have a person who's constantly checking each box as it moves along the belt, but you can probably imagine how tiring that might be. Instead of that, we could totally have a camera that is constantly checking, let's say, it has integrated processing unit and everything, so it can tell if something is okay or not okay, right? So with this, we can decide what to do. We can even move the box away. So we have a rework area where we try to make this right. We have all these possibilities with computer vision because we are sensing the real world, we are processing this information, and then we are taking a decision. So sometimes we are the ones taking the decision. Sometimes we automate the system to take the decision on its own, right? So this is part of the automation trend, where we're trying to take the load off our shoulders and then just pass this to a system that can perform in this environment, in these given conditions. So computer vision is great, something that I really like, and I had the pleasure to work with this kind of systems and to see how it's applied from the pharmaceutical industry, in the packaging industry, also in the adhesive technology industry, and most recently I've been working in robotics. So it's a really exciting field, but at the same time it has some challenges that of course requires to adapt the solution to your need, to your problem. So the thing is, computer vision can be sensitive, for instance, to the varying conditions. So when we have workarounds, of course, but lighting is important. It's really important in computer vision. So when we have, for instance, bad lighting, or we have inconsistent lighting, so we have lighting that is constantly changing, or it's so random, then our vision system might suffer. So conditions, it's let's say drawbacks, as I will say. So conditions are important. You have to manage them. There are many ways to do it, but it's essential to understand that there's a limitation, and we have to tailor our solution according to our need. So this is all for today. I just wanted to give you a little intro to computer vision, to what can be done, let's say, with computer vision. Hello and welcome. So today we're gonna work on the key assumptions in computer vision. We are gonna learn about some of the fundamental physics. Then we're gonna learn about the Snell law, which is so related. And then we're gonna also learn light units. Those are the three objectives we have for today. So bear with me, this won't be in deep detail because there are many books that I will give you as a reference where you can just go more into the physics and mathematics if you want. So the first thing that I had to tell you is the light has in international units is candela, so that represents the luminous intensity. This is not the most used in general when you are talking about light. Usually when we talk about light, we talk about other things. For sure you might have heard before exposure, for instance, or luminance or lumens. So when you're buying, for instance, a light bulb. So so in this case, we have these units like luminance and luminous flux that are derived from luminous intensity. And for instance, one represents the luminous intensity per area, right? So this is the kind of units that is used in the terms of light units. As we develop the applications, we will talk more in detail of each one of this if it's necessary. But otherwise, just keep in mind, luminous intensity, we use candela, is the international unit, and then we generally use more lumens. And from lumens, we're talking about also exposure. That is something that we for sure gonna treat in this course. So in general, also light is presents a dual behavior, as you might know probably. It's the light can behave as a particle or a wave. And I showed you this diagram before where we have let's say the spectrum. So we have also the visible light, the range. So in general, light has this behavior, and when you interpret sort of the physical phenomena that is happening, when one of the two might be really easy to explain, let's say, what's going on. So for instance, in cameras, we use something as or in lasers, we think of a particle, for instance. So we use a model that we're going to see later that basically is we assume that that is a ray, so it's the ray model. So we have that the light goes straight to a point, and then it has some response it adds in some way depending on the material. So in general, you have keep in mind this axioms here. So light is an electromagnetic wave, so it has a magnetic field and an electric field. The light presents what we said, a wave particle dualism, light will propagate in a straight line in homogeneous and isotropic media. So this is one of the assumptions that I was mentioning. So we assume that won't deviate, will be straight. Then we have refraction and reflection occur at the boundaries. The velocity of propagation is dependent on the cross medium. So it means that the light speed is not constant, it's not the same, will depend if you're in water, if you're in air, or if you're in the vacuum. In the vacuum, for instance, is this value we have written here on the right. And then there is no interaction between the light of different sources. There is a common assumption that is made in machine vision applications. Because keeping these interactions, and let's say, of course, you have to experiment, you have to see how the light is acting on your object, but still, it's very unlikely that you're gonna take a formula and just try to predict, for instance, how the lights are interacting at some point. It's usually optimized. Usually, we have algorithms that we create that are not so dependent on the light conditions. Let's say they try to be as independent from the light condition. Of course, if we have extreme changes of light condition, we will have problems most likely with the vision application. So that's one for sure. Then it's a simple equation that we have that relates the speed of light with the frequency and the wavelength. So here we go. So let's talk about light with objects, right? So we know the light will, let's say we have an incoming light, as we show here, and then we will have different behaviors. Here I drew some of the, let's say, behaviors that we expect from light. It could be, for instance, direct reflection or specular reflection, this is known. It could be scattering, it could be absorption, it could be transmission. So in general, we have that in the light, we have reflection, transmission, and absorption. So the conservation of energy says that this incoming light should be equal to all of these components. So thus this formula that you have here under. So let's look one by one to understand how light will act when faces an object. So the first one is reflection. So we have, for instance, directed reflection that is more like a mirror, where you have very uniform, the light comes in, comes out, no issue. We have also regular diffuse reflection, which the light comes and then, let's say, reflects uniformly through the surrounding. And then we have irregular diffuse reflection, which the light has a particular direction, let's say, where reflects more. The truth is that you, in a computer vision system, you usually have multiple cases of reflection. You will not have just one. It depends on the object. For instance, here, this is my camera. And as you can see, there is a very bright part that correspond to an specular reflection. Then you have other parts that reflect differently. So it really depends on the lighting, how you position the lighting, and also as you see, this will change the brightness of the image. So it's something that we have to keep in mind. It's something important. Then we have transmission. Transmission has relevance in diverse contexts when it comes to computer vision. So, for instance, when we are dealing with transparent material or backlight applications. So transparent materials, for instance, are common in pharmaceutical industries. I think in packaging as well, there are some cases, some special cases. So it really could be that when we have this transmission, we could have different cases. So we could have direct transmission, we could have an irregular diffuse transmission, that it's similar to the concept of reflection, where we have that it goes more in one particular direction, so to speak. And then we have diffuse transmission, which is more uniform. So then we have a Snell law that what it represents is that, or what it says is that, of course, as you know, when we, because we just said it, is that the light changes depending on the medium, right? This is one of the axioms we said before. So, for instance, when you are changing from one medium to the other, you will have the speed of light will be differently. So, for instance, here we have that it relates the incident angle with the exit angle. So, and then we have two values there. That is n1 and n2, and is what is known as the refraction index. So for different elements, you have the refraction index. So you have for water, for liquids, for any type of liquid, for gases, you have different refraction index. So with this, what you can know is basically, if you know how the light is going to impact with some given angle, you can predict, let's say, how, what would be the behavior. Then we have also this part that is also important, and is that some of the light will be absorbed by the material. So in this case, this portion of light will transform into heat. So usually it's very complex to compute. One approach will be just simply that the formula we have. If we know all the other parameters, we can compute the absorption. Then we have diffraction. That is something, for instance, that is really important when we're working with monochromatic light. And what it will cause is that we have the image quality will be reduced. We will have soft spots. So in general, diffraction occurs when light encounters an object and it has a small. Hello and welcome to image formation in computer vision. We're going to explore today the model for image formation. We're going to also see the coordinate transformation and camera calibration process. So firstly, we have to understand how the image formation works. Firstly, what it is. So in terms of the 3D world coordinates, we have specific points, x, y, z, to define, according to a reference, a specific point in the space. So what we do with image formation is take this point and map it to a 2D image. And here, for instance, we're doing that. We have some important transformations that we're going to see. And also, this point is very intuitive, right? Because you have your phone camera and you know that when you are taking a picture, you're losing some information. You can sort of have some concept of what is, of the 3D, but with the simple image, you're just passing everything to a 2D image, right? So that's the process. Then we have a very idealistic model, which is the pinhole model, where we have the object here, and we have that the sun is shining this object, and then we have the light rays will reflect on the surface, as we studied before in one video, and then we will have that the surface will send these light rays through this pinhole. In this pinhole, we have it's a good gathering, it's a perfect gathering of the light. Well, we have that on the other side, we will form an image. So the pinhole model can be thought of, we have a 3D point, x, y, z coordinates, And then what we do is through the center of projection, pass all the rays. This is the optical center. So we pass all these rays, and then I'm just plotting here one single ray where we can see that there is no bending, it's just a straight line. So, I mean, it should be a straight line. Of course, my drawings are not the best, but just imagine it's a straight line. So what we have is that this point in the image plane, where is the plane where we form the image, it will be a point, P, this is lowercase p, and we have any specific coordinates. This model of image formation allows us to predict where are these coordinates. And this is the equation you see here. So this x lowercase is relating the focal length, which is the distance here, to the information of the 3D world. The same does y. So now, as you can see, we have two coordinates to describe this image plane, and it makes sense, right? Because we are mapping this 3D world to a 2D image. So that is the projection model that we're using. Then it has some implications. So one of those is that objects will appear smaller as we increase the distances. And we also know that intuitively, when you use your phone, you get closer to an object, or you go further away if you want to have like a larger view of the object. Then we have also the central projection, as I explained, everything passes to the optical center. And what we talked so many times already is the 3D to 2D information. So when it comes to this transformation from the 3D world to the image, we can define a model for that. So where we have that we take these world coordinates and we pass it to a distortion-free image. For that, we have something where we have the transformation that implies we take the world coordinates, we move this, we have a rotation and translation with respect to the camera. Then we have the projection, and finally what we will have is the transformations that allow us to have these coordinates into a 2D pixel coordinates. So these will be basically coordinates that we will use for further analysis, right? So something important in this projection model is the K matrix, which is related to the parameters of the camera. So we have some parameters, like, let me just go here, where we have like the principal point, we have the skew parameter, and we have also the focal length parameters. All these parameters must be determined through calibration, which is a process we will see in a bit. So then here we have the other parameters that are extrinsic to the camera, and we have that is the rotation and the translation, which indicates the orientation and position of the camera coordinates relative to the world coordinates. We can also write this in such a way, where we have the rotation and translation integrated into a matrix. So before I jump into the lens distortion, we have seen so far that we have the this model where we have the transformation to the 3D to pixel coordinates to a distortion-free image, sorry. And in this process, if we consider not a pinhole model, because most cameras, as you know, won't have just an aperture like this. They have lenses, they gather light, and these are not perfect. So when you have lenses into the equation, that is basically for all the cameras, you also could have the effect of distortion of the lens distortion. In this case, we're talking about, for instance, there's some models that will help us to determine let's say the distortion parameters that will allow us to come back to the original image to get a actual, for instance, if we think of the grid, we have this grid should be like this. We have a 2D image, but instead it comes like this, maybe, or like that. So what we do is to find these parameters that will allow us to come back and to transform this into the original image. So this is important because, as I said, we have lenses. We don't use just a pinhole to gather light. So let's say we obtain an image. How do we obtain this image field distortion? We have to calibrate for sure in order to get the information needed to perform the forward projection model. So imagine the steps are like this. You first find a checkerboard, just a pattern, like a sort of chessboard, similar, where you have the information. You have all the points, intersections. You know them accurately because you know the dimensions of the grid. So you can then establish the 3D to 2D correspondences, or between the board and the camera. And what you can do is to solve this system in order to find the parameters that we discussed about before. So we're talking about rotation translation, and then also we're talking about specifically the camera matrix. That's the thing you want to find, the K. So one method to do that is the direct linear transformation, DLT. And what we do with that is to, let's say we think of this equation. We are relating the 3D world to the 2D image coordinates. So we have this is the sensor image coordinates, and we have the scale factor, we have the projection matrix, and then we have the XYZ. So the projection matrix, basically, as we said, is helping us to literally project the 3D world to the 2D image. So whenever you see this P, it's for that purpose. And then what we can do is we can divide this form into these three equations. Then by diverse, let's say, operations, we can obtain this form. Then we have to, when we proceed to linearize this equation, we'll realize that for each point we will have two equations, and then we need at least 6 points in order to obtain all the parameters of the K matrix. So then this is not the only DLT is not the only method for calibration. There are some others like the ZAM method. And as I said, we need a minimum of 6 points to solve the linear system. So there are different methods that we're not going to go into that. At the end of the day, it's a workshop. We don't want to keep information precise and then just focus on the actual output of the project, applying this knowledge, let's say. So then we solve this system, and we should be able to attain the parameters of the camera. Thank you for taking the course. You're halfway there. So I know theory can be a bit daunting, can be a lot of information just compressed, but you are doing great. We have just 2 more lessons on the theoretical part, and then we're going to jump straight onto the application. We're going to build something small, something that will help you to gain some foundation. The main task what we'll do is to classify images. Thank you very much. Keep going. Hello, welcome back. So today we're going to review the hardware technologies in computer vision. So we're going to look up to review some of the various hardware available for computer vision systems. We're going to learn, we're going to see some cameras, the main underlying hardware components, and then we're going to see also what is out there in terms of computer vision. So it will be a brief introduction to the hardware aspects. So let's begin with the camera's technology. In general, a camera has the lens, has image sensor, and also we have the shutter, we have an element that is controlling the aperture, we have the body and the battery and so forth. This is just a general camera. This is, for instance, this is a Japanese brand. It's that we have also Canon and the lenses. They usually come with a C-mount. You probably know that these cameras are used in different contexts. More for imaging, that is still part of computer vision. But for the type of applications, let's say, that are more automatized or are more like for robotics, these are not the type of cameras that are used. Nevertheless, the concepts more or less remain the same. So we have the lens will help you to focus the light onto the sensor. Then we have the image sensor. We have most of the cameras nowadays use a complementary metal oxide semiconductor. And then we have that there are different elements across. So let's start with the sensor. This is the charge coupled device, which is more like an old type of sensor that is not really used nowadays. But I think it's good to understand more or less how it works, because it helps you to compare like the alternative, that is CMOs. It allows you to understand why we use the other one. So the working principle is basically, as we said, the light is the one that is communicating everything. So with the light, we create an electrical charge. Then we transfer this charge. We have, for instance, register of the different charges, and then we output this into a sensor capacity circuit, where we're gonna have that we will output a signal that will be fairly low. So we will need like a signal amplifier, and with this we have some advantages when it comes to generating an image. And the first thing is that we will have higher quality image with less noise. We have more light sensitivity, and generally is more uniform response. The disadvantages, it's the speed is fairly slow, and then it also consumes a lot of power in comparison, let's say, to the one we're gonna see next. So in general, we have the light striking the photo size, and then we have the effect, the photovoltaic effect, and this creates, we are able to pass this photo energy into a signal. That's the whole process. There are many ways, variations even across the registry of this charging, but at the end of the day, the concept is the same. We're transforming the energy into a signal. So this is the most used nowadays, which is the complementary metal oxide semiconductor, and this one it's able in each of its pixels to charge to voltage conversion. So basically can convert, and then we can read directly from each pixel. So in this one we don't have to do this registry that we saw before. So in all, will be faster. It also has lower power consumption. Is less expensive, tend to be less expensive to manufacture, And then it's suitable for high applications, which nowadays is one of the key, let's say, at least in the industry, manufacturing industry. So disadvantages is that in general we can have more fixed pattern noise, and the quality of the image tend to be lower. But as I said there, we are closing the gap. So now we have very good quality with this type of sensor. So another point that is interesting is the shuttering process, that it allows us to control the exposure time, and those we are controlling the amount of light that we are receiving. So this is one neat example that shows like we have a fan, and imagine if you are taking the processing the images by individual lines. If you're doing that, you will have, for sure, you have a lagging time, and therefore you will have the effect that you show there. That is not a real, it doesn't correspond with the reality, because the object is itself is not deformed like that. Then we have the global shutter, which allows us to take motionless pictures like this. So where we do not perceive, like we perceive the object as it is without these deformation for the shutter. But this deformation is basically just because there is a lag in time and we are exposing individual lines. So in general, when we talk about image sensor, we have some key parameters. So for instance, we have the resolution that will tell you the number of pixels. You hear around megapixels when you're talking about your phone. For instance, you find a camera of 50 megapixels or something like that. Higher resolution will generally have more details, but also if you have bought a mobile phone, you also know that higher, like a lot of pixels doesn't guarantee a good photo. So this also to keep in mind, because doesn't necessarily imply better image quality. And also we can introduce plenty more noise if we don't control the post-processing as well. So then we have also the pixel size, which is measuring micrometer, and from this we can also compute many of the parameters that we're not going to do here, because this is more practical course. Lastly, we have this. Also, we have the sensor size, which generally a large sensor size will produce better image quality. And also something important when we talk about sensors is the dynamic range, which will help you to distinguish, will help you with the contrast of the scene. But these are not the only sensors we have. We also have like infrared for thermal imaging. We have X-ray, where we can generate the map density. We have radar. We have MRI for tissue density, and we have also gamma maps even. So the possibilities of applying these tools, of course, depends on the specific case, but this is just a general review of the type of sensors we have. So in general, cameras are using many fields. For instance, here we have the Raspberry Pi camera that is small. It's the one that we're going to use for the project, but let's not go to that now. So then we have, of course, we have the applications could be many. So we have in robotics, we have, for instance, for inspection, we have for drones, for augmented reality, educational projects like the one we can develop. Then we have also, as I said, in manufacturing quality control, and all of things regarding with high speed, because high speed usually is fairly challenging for our eyes. So cameras can help us in that case. But there is more. We have also 3D imaging. So we have We have technologies that generate a cloud of points that we have to navigate the world. So it's using autonomous vehicles like light detection and ranging. And we have also a stereo vision. We use 2 cameras. We have a structured light and time of flight sensor. So this all allows us to map the 3D world. There is also the hardware for computer vision. So we're talking about we can use general CPUs, we can use GPUs or vision processing units that have been that can be used for are optimized, let's say, for computer vision tasks. Something very, very important that I love for this part is illumination. Also, illumination is essential, and it's unlikely that you're gonna get good results if you don't have decent illumination. Either natural sources, or you can have like illuminators that are very common in the industry. Another one is to have smart cameras that they have integrated these illuminators, so it is needed in order to be able to process this scene. And this makes sense, because you have that the light is the one that is communicating the information. We are transforming the energy from the photons to the a signal, so therefore you need to have light. So now let's talk about image data processing. So we will understand the digital image representation and some properties, and we will see some of the fundamental statistics used in image data processing. So an image data consists of a grid, and this grid has some columns and some rows and some grid points. So in this data is represented by, for instance, we can do it more formally, write it like this, where we have also some channels. So we have the channel intensity, which depending on the bits of the image, so the most common is 8 bits. So we have from 0 to 255, where 0 is black, 255 represents something very bright. We also could have this image, doesn't necessarily have to be 8 bits, it could be binary too, so we can have a 0 or 1. And also something that's important is that specialized medical applications might use more bits. Then something that you might wonder is in the case of images where we have color. In this case, we can consider it's similar. We have a grid also, but the grid is extended. So we have 3. So one is red, one is green, one is blue, and this generates the color space. In this case, we have that the image dimension is expressed as m times n. So they are, in terms of the size, they're the same. The only thing is changing is the intensity across the different ones. You can have, for instance, the analysis of the red, the analysis of the green, or the analysis of the blue. So it's possible. Then something that we can do is to have to understand about pixel manipulation. So for pixel manipulation, we can, for instance, increase the brightness of a pixel, performing this operation here, or we might even increase the contrast of this pixel. For instance, this is a photo I took, and this is I'm adjusting brightness here, and you can see the difference. So this is a common, let's say, manipulation that you can do to the pixels, so such increasing brightness or contrast depending on the task. Now let's continue with the colors So we talk about the RGB, we have talked about grayscale, and also binary. So there is a transformation between the gray. For instance, if you have 3D color and you want to have it in the grayscale, there is a transformation that is possible. That is this one here, that is sort of weighted for our vision as humans. And then we have that RGB is not the only color space. So we have also HSV and LAB, also color space. But for instance, so far most of the applications you will see will either use RGB or HSV. So when it comes to statistics, in order to perform or to understand the characteristics of an image and to help you identify certain features or detect some anomalies, we can compute the mean of the image. So in this case, we have the image XY, and then we can sum all the columns and rows and then divide it by the number of columns and rows, and we will have the mean. Slightly sort of similar operation to get to the variance, and then we have the square root will be the standard deviation. This will give us an idea of the uniformity of the image, if we have a high contrast, if we have a low contrast, or we have a very bright image, will give us that perspective. Also, another tool is the histograms. The histograms represent tabulated frequencies. So for instance, what we do is take the image, get the intensity, and we take the values. For instance, if we have an image that is very skewed towards the right, it will mean that this image is probably very bright because we have a high frequency on that side. So what we do is to plot on the X, we plot the intensity level, and on the Y we have the frequency. For the histograms, what we also can do is to obtain a probability density function, where we go from 0 to 1 in this case. So we just take the histogram and we divide it over the image space that we have. And what we have is that we can compute also the mean and the variance. Once we compute the variance, we can compute also the standard deviation. For instance, this is one photo that I shot a couple of days ago, and you can see, for instance, the grayscale, how it shows, and we have the mean not normalized is 133, which indicates that we have relatively well exposed image. And then we have a standard deviation of 66. So it indicates we have good contrast, which it seems the case. So this is just a tool to have information of the image. It will not be the end of the analysis. This is just a starting point. We will not be performing this kind of analysis in the course, because we're doing something very practical, but is it also essential to understand some of the tools, let's say, that are used in the understanding of image data. Hello and welcome back. So let's start by reviewing what we saw in the last session. So in the last session, we studied image digital data, and we saw how we can obtain some information of our image. We also saw about the color space, and today we're gonna connect this to a fundamental question. It is how these machines can interpret, can understand the world, and can take meaningful decisions. So we will explore some traditional methods, and also we will explore some deep learning methods. So let's start with the traditional computer vision. So these traditional methods rely on precise analysis to select the correct image processing, feature extraction, machine algorithm, and it's very reliant on the application. So it's not very flexible. It's not, let's say, it's not general. It cannot be applied to all cases. So these applications tend to be less demanding when it comes to computational power requirements, and the traditional steps are 4. So the first one is where we do some image processing, then we extract some features, and then we do all the feature matching and classification. So when it comes to image processing, there are multiple techniques and methods. Among those, I show you here the application of the Gaussian filter to reduce noise. That is one of the first things you do, especially if you're going to apply edge detection method, because they tend to be they're very dependent on noise. They're affected by noise. So there are many other methods available. Most of the time you don't have to develop the method yourself. You have OpenCV, MATLAB, all of these tools, Wolfram Mathematic as well. All of these tools have integrated image processing toolbox that you can use instead of sort of reinventing the wheel. So that's the first thing you want to do in those cases. Then you want to understand what is the feature space. So this feature contains all of the values that you find important for your processing, for your image processing. So we can be talking about the area, the length, the color, the grade level values, the entropy. So you want to ideally find, let's say you are classifying objects in different light conditions, you want to ideally find some features that are invariant. So in the sense that they don't change from because you changed the illumination, or maybe because you did a little bit of zoom. So it's tough to find the correct features that you need for each application, and that's why it usually requires quite some engineering these methods. So another aspect that you have to keep in mind is that when you are using too many features, you are increasing exponentially the computer resources, and it doesn't necessarily guarantee better results. On the other hand, if you're using just too few elements, you can get fairly inaccurate results. So it's with experience, of course, you can find these values, some methods to extract the features. So here the goal is to select those features that are effective for discriminating, for instance, between different objects. So methods served are available, and they allow us to this method allows us to identify the distinctive points in an image and extract the features descriptors. Then you can use that to match the respective categories, or if you're classifying between objects. So there are many other algorithms. I'm just telling you something very general, sort of to understand the process. And then you come to the last part where you are classifying, where you're matching and classifying. So let's say you define the specific details or the specific aspects that make one object different from the other. So you create the categories. This is an essential process when we are talking in computer vision. You, based on your intelligence, you define what is the or your data. Also, you define what is the the categories. Maybe you are classifying different type of defects. Maybe you are classifying different type of objects. So it really depends. Then we can use methods such K and N to identify, let's say, objects that belong to certain category. And the process, it consists basically in first finding this value that you want to, how many near neighbors need to be considered. Then you can calculate the distance between the point of interest in the neighbors using, for instance, the Euclidean distance, and then you can verify which one are close enough to be considered in this specific category. There are many other algorithms to do this process. So let's go back to one of the most interesting aspects that we are probably more interested in, and is deep learning based methods. So deep learning uses neural networks with multiple layers to automatically learn features and perform specific tasks. So in computer vision, often convolutional networks are the cornerstone, and they have different elements. So for instance, convolutional layers apply different filters to create feature maps. Then we have the pooling layers, which this can reduce the spatial dimension of the feature maps, because as you create this convolution, you have applied this window through the image, you create many spatial dimensions that will, with downsampling, you reduce the computational load. Then you have the fully connected layers that they usually are at the almost the very end, basically, of the neural network structure, and they help us to classify the respective objects. Then we have the activation function, which there are many, such ReLU, such SIGMOID, and these introduce nonlinearity into the neural network. And this allows to have more, you might wonder why we will introduce this nonlinearity in the neural networks. And it basically what it allows is to help us learn complex patterns that not necessarily follow a linear, let's say, approach. So they are essential. And then, of course, we have the training and optimization. So, for instance, the network is trained using backpropagation and gradient descent to minimize the loss function. And this helps us to adjust the weights and biases to improve the performance. So you might say, what is all of that? So let's just see a graph to help us understand what is that. So imagine you have an image. So you have m times n image, and then you have this RGB image. Probably you have different, as we explained, we have different channels, and then you are trying to classify. So the neural network will look something like this. You first apply a convolution, you then do some downsampling, then you might apply another convolution, or maybe even another one. And then you have some pooling after a convolution, and then you have the fully connected network where you finally will output and will classify the images. Of course, we're not going to go deep into theory now. This is just to give you a general perspective. We are going to be applying this knowledge. So we're going to be building one neural network like this for the project. So just be patient. We're going to get there very soon. So you might wonder which one to use, which approach. The answer will be, it depends on what you want to do, on your resources, data requirements, flexibility, development time, and so many other aspects. The important thing is that one of the key aspects when you are trying to decide this is that not necessarily with improved, not necessarily AI using neural networks, will guarantee the best compromise when you are working in computer vision. So it really depends on the kind of equipment you have and how much resources you have as well. So in this course, we will use deep learning based approach because it's fairly flexible. If enough data and proper training could be really good, can have really good performance, and on top of that, very flexible. The truth is that it will be very cumbersome to do the traditional approach with the project we're going to build. So we require something very flexible, and also will allow us to implement this in a edge mobile application. So it will be fairly interesting. Hello and welcome back. So today we're gonna start with our project officially. So we are gonna classify trash. So the answer or our project will answer the question, which type of waste do we have here? So for instance, if you look on the right side, we have mostly e-waste. So we could say that we can classify this as e-waste. On the other hand, on the left, we have mostly paperboard. So we gonna classify it as paperboard. Of course, this is just an example, and usually most of the images you see probably have many elements. So, or it's more complex to understand what it is. So that's what we're gonna do. We're gonna train a neural network that should be able to run very efficiently on edge devices. So this, as part of the more advanced continuation of this workshop, there is the integration with Raspberry Pi and all the setup, the development, and so forth. So then what is the strategy? So we want to know what is the main object on the image. So we will use some of the tools here, like of course Python. We'll use Tensorflow, Matplotlib, some Python functions. And the process will be, if we could summarize the process, would be something like this. So the first thing we're gonna do is to set up the development, to set up where we're gonna work. You're gonna see that it's relatively easy to do and quickly. Perhaps you don't even have to install anything if you don't want to. Then we're gonna find and process the data. Third, we're gonna build our module. Our model. So this model is based on a technique that I will show you just in a sec. And then we're gonna train and export this model. Then you're free to do all the testing you want and to see how it performs. And while we have some data, transfer learning help us. Transfer learning consists in using part of an existing neural network that was pre-trained, that was trained on perhaps a larger data set for sure in this case. And we take these feature extractions and we, let's say, append it to our classification layer. We're gonna do that. It's fairly simple. But then what I'm showing you here, MobileNet, is one of those neural networks. And this is, you could have ResNet, you could have MobileNet different versions, you could have Efficient B0, I think is the name. So then you have many other architectures that you could use. MobileNet is specifically designed for mobile edge devices, so it does prioritize efficiency and speed, with some compromises when it comes in terms of accuracy. But for, let's say, the idea of the project to eventually integrate this into an edge device, a MobileNet is reasonably it's a reasonable compromise, let's say. So then transfer learning has also three main advantages. And the first one is it helps us reduce the training time, because we could even try to train it, and it will be a nice exercise that I will leave for the continuation of this course. But then to compare, like, how much time are we spending using this transfer learning technique versus just having a simple structure of a convolutional neural network. So then, beyond reducing the training time, also help us improve performance. These architectures have been trained on large data sets, and this help us to have a more robust architecture. Then we have less data is required, and in this case we have that we train our data set is relatively small, so, and it's fairly complex, it's trash on its own is a bit messy, so this creates a huge challenge. So transfer learning helps us to get there faster, right? To get to decent results. One of the areas that we can improve this project is by changing the question. Instead of asking what is the main element on this image, we could ask how many elements of a particular type are present. So, for instance, e-waste or plastic. So, depending, of course, on the type of question we ask, the solution takes a whole different approach. So in this case, if you want to count and classify each element in the image, we require a different approach. So we're starting from something basic as identifying, let's say, the main element. Hello and welcome back. So the first thing that I will show you is how to set up your environment. So this is one of the fastest and easiest way to run, I think, your code, because you don't have to set up anything. Then in the next video, we're going to see how to set up using Ubuntu, your working environment. But here, you can use Colab by Google, and it's a great tool that will help you to run all your code, and it's something that most people use, let's say, when it comes to handling vast amount of data, because most of us just don't have the possibility of having maybe a server available all the time to run our codes or analysis or our training. So it's a great way, let's say, to run it on the cloud, so you are so you don't, let's say, so you're able to run your process faster. The pro is that it is free to use, and you have the possibility of using GPU to accelerate the training and so forth. The cons is that the resource, of course, is not guaranteed. So you don't have, let's say, all the time available the GPU. It really depends on the demand of Google Colab at that time, right? With that being said, something I don't think might be necessary to go through the whole user interface, but what I want you to see is that you can create a new notebook here, so you can start coding right away. I don't know why it looks like that, sorry. You can start coding right away here so you can see it's running here. Then on the left side, you have the files. So here you will handle all the files. You can upload files. You can connect to Google Drive as well to handle the data. And something important is here. It's located right here. The runtime options. So the runtime options will allow you to see because by default it will just use CPU, so it will take some time. But what you can do here is to change runtime type, and as you can see, you have the different kind of availability. Of course, if you purchase, you get the possibility of using T4 GPU, for instance, which is which is one. Then you have this one, it's TPU. Also, you see there are other languages such as Julia and R. So there are many possibilities here. Just be mindful, select the run type, because it will only give you CPU and the computation will be significantly slower. So just go for this one, T4 GPU, okay? With that said, you can just run your code here. You have some information regarding the RAM and disk. So when it comes to Google Colab, something that you have to keep in mind is your information. Where do you save all your files? How do you run it? Here is just a screen of what I have. So you can create your notebook where you have the sort of the procedure of how your code runs, but then you need to have the files. So I suggest you save all your files in Google Drive, and you can use this code from Google Colab import drive dry mount to mount your project. So it will immediately ask you whether you want to connect your Google Drive or not, and then you can navigate to your specific folders. So for instance, I use here %CD, and then I go to the specific folder where I have all my project, and then I can run it just by I can just run Python, run any file that I want by simply adding this sign at the beginning of the Python file I want to run, or the execution I want to do. This is essential, of course, because you want to have your files saved and you want to have all your files organized. So just use Google Drive and you can mount it very easily, as you see here, just by typing this command. And then you can do the normal operation like go into the file, or also execute certain script that you want, or you can just type the function as well. Hello and welcome back. Today we're going to do something extremely important, and is to set up our. So for that, we're going to use, I'm going to drive you to every step that you will need to leave your Ubuntu installation working and ready to develop the project. So the first thing we're going to do is we're going to go to Firefox, and then we're going to go Conda, download. We can then come here to download. So, or you can just come to the website and conda.org, and then you will come to download. You can just distribution installers, then you press Linux, and then you get here the 64 bits install. So it might take a while to download. Then what you're gonna do is to open the terminal. You will open the terminal. Now that we have downloaded the file, let's just go to home. And from here we can go then to downloads. We should be able to find the file. I already converted it, but you can do this. You can type this command and then just type this just to be able to execute this file. Finally, you can then run the file. So you can then do this, and we will continue, and we read the general documentation, user agreement. So now I'm gonna say yes, and I'm just gonna let it to install in the home, my username. So just don't modify anything here. Let's allow that. So now it's gonna install all and extract all the components necessary to work with Conda. So now I will say yes, and we good to go. So I will just close this and open the terminal again. You can see here that is already indicating that it's using Conda. Let me just type Conda info just to know more if we have a successful installation. And we do have a successful installation. We have here the Python version, we have the Conda version as well, so we are good to go in these terms. So now that we have checked that we have Conda, we can proceed to verify which environments we have. So we can write Conda m list, and we see that we have only one environment, the base, but there is a possibility of creating new environments. So how do we do that? We can Conda create, and we're gonna name this however we want. It will be project, course, something like that. And here we're creating this environment, and I want to say yes, and we should be able to have the environment. Now we Conda m list, and as you can see, we have two environments. So in each environment, we will install the kind of programs that we will need. And for instance, we will do that later as we require, but then we can, for the time being, for instance, I could create here, I could just come back quickly here, and I could create another one. Let's say, let me say trial, and then I will create this one with Python, let's say 3.5. So I'm going to say yes. So it should be done now. So here we have the packages that we install, and here we have Python, as you can see, 3.5. We have created our environment named trial, where we added, we have one specification, which is Python 3.5, and we have finally installed our environment. Now we will go to try to obtain the coding tool that we will use. In my case, I like Visual Studio Code, which is this one here, and from here you can just install it directly. So it shouldn't be any problem so far. That way you will have vs install. So here we have the environment. Now what we want to do is to be able to run our code through this VS Code. So let me just go here and create a new folder. We will create a new folder here where we're gonna save our projects. Then I will create, I will open it. Then I will create a new file, which just will be yes, I trust the authors. And then I will create a new file under trial, like hello Python. So I will just So once you have your environment set up, you can select this environment in Visual Studio Code. How do you do that? You can come here and just type this, and you will see Python select interpreter. From here, you can have then the different environments that you've created. So I always suggest to create one environment where you store all the Python, the packages that you need, and don't use the base. Okay.
So just create the environment, whether it's testing, whether it's object recycling environment, or however you want to call it. And in that environment alone, you will install all the packages needed. So you can install, I don't know if you want to use OpenCV, if you're going to use TensorFlow, for instance, that is one for sure we're going to use. So TensorFlow and Matplotlib. We have also an image processor that is PL. So all of these elements that you need to install it in the specific environment. For TensorFlow at the time of this video, the 3.12 works very well, but you cannot get the last one. So for instance, the base environment you can see is coming with the last version of Python, or at least I installed that one. So it will not work. It's not compatible with the TensorFlow. For this is very easy in terms of which Python version you need to use. You just need to go to the package website. So in this case, TensorFlow, and check there the specification. So what is the minimum requirement in terms of Python? So I never suggest installing the last version of Python because sometimes might not be compatible with the specific modules that you might use in your software development or in your computer vision application. So with this said, you select the environment and you can run your code. Another thing that I want to do in terms of like having a good experience with Visual Studio Code is using these AI tools, right? So for these, one of the one I suggest is Windsurf. I'm not being paid, of course. I'm just suggesting something that I found to be extremely useful. It's not perfect, but even the free version is extremely useful. So for that, you can come here and you can Windsurf. And you can install is you can register on the website, and it's a auto completion tool. So it really smart, and it will sort of help you to complete faster, to type less. So it's fairly useful. So if you want to solve it, I think it's a great tool that will help you just be faster, especially when you have to write things that are the same. And we actually gonna do that in the computer vision course, and you will notice why it is useful. So get this one a try.
So the structure will be fairly simple. We will have 3 folders. So we will have the folder which contains the data. So we will create data here. We will have another folder which contains all the regarding the models. And then we have a folder that is named, oh, sorry, it shouldn't be there. We have here another folder which is gonna be CRC. So we have all the main scripts and all the main Python files. So this is a simple configuration, and another one that we're gonna, oh, sorry. Let me just, okay, there we go. We're gonna have the config folder. So these 4 folders are gonna facilitate the navigation through our project, and we'll make it easier to find errors along the development phase. So let's start by defining, then creating an important file, which is here in config. You're gonna come here and create a new file, and it will be config. So this file contains all the configuration for the models, all the data path, training parameters. So everything is just here. So you can see already the benefit of just having to change one thing and then immediately your code updates, because you make it sort of parametric. So this is the configuration. We're not gonna like create it completely right now. What we're gonna do is only set up the set up 3 important parts of the configuration. So I will say this is the config, and this has all the configuration and different settings for image classification. Then we're going to have the paths will be the first. So we're going to have all the paths to the different folders. Then we're going to have also the model parameters. So we're going to have model parameters. Okay, so let's talk about the setting up the environment. You have available this summary where you have all the main codes. So we're going to look at the Conda environment, and we're going to create an environment, which in this case will be testing. I will create testing, but you can call it the actual environment because I already created an environment, or named object recycling in this case, or object classification, image classification. You can call it as you prefer. Then we have Conda create name testing. So it's going to take some time. It's going to tell us where our environment is going to be, and we say yes. So that way we have the environment. And if you take Conda activate testing, this for sure cannot write Python because Conda works with other languages. So it means we have to install Python. So we can say Conda install Python, or we can type the specific version we want. So I'm going to say yes to that. And it's installing Python. Sorry, which version is it? 3. Okay, so let me just check. It's 3.14. Okay, so I'm going to activate the environment that we just created, that is testing. And I'm going to conda install Tensorflow. I'm using, we have conflict in the Python 3.14. And we're going to say yes. And with this, we have the main tool we need to run our code. Basically, the main package that we're going to use. If we might use another package, you could add it just as simple as showcase, or you can say pip install and the different, for instance, pip install, this is important. Matplotlib, just the one we're going to use for all the plotting, all the showcasing the results of the training. So one of the first things that we're gonna set up is our dataset. So this dataset is already created. We're not gonna spend the time to find the dataset for this sort of basic project that we're building. So what we're gonna do is to use this dataset that you can access here. This is the address, and then can be used for as it says here, for object weight classification. So as you see here, we have then the information. Here we have that it has 7 categories. So we have medical waste, we have e-waste, we have plastic, paper, metal, and also at the same time is subdivided into the specific device, right? So we will not go into setting up to that level of detail of saying this is bottle or this is container. We're mostly thinking of recycling. So when it comes to recycling, sometimes, especially when if you look around some countries in Europe, you have the paper, you have the plastic, you have the glass, so you separate those. So this is the idea. So we have something that can help us just do a little bit of recycling. So we will download this. So from here, you can simply go to code and you can just download all the information, or you can also do in such a way, cloning using this URL. I'm just gonna download here. So I'm now in the data folder and I will put this zip file there. We're gonna organize it in a bit. So it will take some time to download, so just be patient. So now that we have this data available here, we can go to trash. We can zip this for sure. We have test and training. So in training, we have different categories. I chose 4. Like if you're training on your computer, you can choose less categories or the ones that you're interested in. And then you have the testing where you have the different categories. So you have basically these 2 folders, and that's how your data folder should look, minus this. So this is just the categories that I don't want to have for the moment, and I moved them here. So we're gonna focus on our config files. So let me just to review a little bit the folder. So we have the project recycling and we have the configuration file, which contains also the data. I have no idea why I put it like that. So what I will do just to move out the data outside, just to wanted to make it somehow cleaner, but ended up doing it just a bit probably confusing. So I'm gonna move the data out. Just gonna leave it here as it should have been. So we have the config, the data folders. We have these 3 folders, right? As it should be organized. So we have the config file, and we start with stating what it is, and then we have all the configuration, different settings for the image classification will be here. And what we have, for the time being, don't mind this information, but we will set the location of the data directory, some directories we want. The essentials you need to have is basically the data directory, the train directory, and the testing directory, and this one here. So what we're gonna do then is to proceed to input the model and data parameters. So we have the image size, validation split, batch size, input shape, epoch-based learning rate. So you can just put these values. You can leave this as it is showcased here. You can leave the validation split at 20%. And you can maybe reduce this to 32, and we can reduce this to 001. And you can leave this to 10, just something very, very, very short. And we can save this. Then we're going to go to the config file. So the config file allows us to have this text information that you are probably aware that this is not a valid Python file. This is not the way to create a list. So we go to the config file. So the config file is a script that is always located here, and it will allow us to transition from this information to Python. So this is the import, where we import in order to be able to read this type of file, and we need to import this function that is the path. So the first thing you're gonna do on the project is to define the root path. Without the root path, you cannot. It will be very difficult to handle all the files and how are gonna be organized. So you need to define this first. So what is happening here? We are defining that the path of this file, the configuration. Let me add also that if you don't properly select the path, what will happen is that it dynamically changes sometimes where you run the code. So it will be for sure will crash at some point. So that's why it's important. So you have the path and you have the file. So this file is the config, right? So it's saying I have the config file, which is here. Then I go to the parent. So I go to models, and sorry, I go to the pattern, which is SRC. And when I go to the SRC, I go even more, and I'm in the root folder, and it's true. So this is my project root path. Anyways, you can go to the config path, which is the configuration we want to set up. So what we're saying is, if you're under the root path, if you go to config, and to the folder config, and then you can find the config file there. So this is correct. And once we find this config file, we can open it. So what we do is to go to this path, to read it, and to save all this data here. All this data available, we save it here under data. And now is very simple and repetitive. We separate the paths and the models and data parameters. So in the data directory, we're saying, okay, so the project root path, and we're gonna obtain the data directory. So basically everything is with respect of the data directory. So in this case, then, sorry, let me just take these models out. So in this case, what we have is that we need to configure this data in such a way. So for instance, the data directory, where is it? The data directory is under data. Does it? It's just right there. Then we have the train directory, which is data training. And we have the testing directory, which is data test. If we look at that. And this will be for later, but I will just do it anyways now. So this should be our configuration file. So you can see when it comes to the other directories, it's the same. For the other type of files, we just can get it like this, data get, and that's it. So this is a way to sort of handle the organization of our folder. And for instance, I can add another folder, which is, sorry, the models, model rather. So it is model, okay. So that's it. Basically, we have the config file ready, and we can proceed on to the next one. Okay, so now it's time to work on our data processing. So for our data processing, we mean we have the different images, different files that might be not valid. So since these files might not be valid, might be corrupt, or might not be as we wanted, we have to sort of remove those that might hurt our code, right? So this is the first step that we're gonna do. So for this, in general, as you see, we're starting our file. We're describing where is this file located, and then we're importing the necessary elements. So we're importing the pathlib, we're importing the list, we're importing the TensorFlow, and we're creating a class. So this class is image processor, and this class takes as an input a data directory. So what it does is then to initialize certain configuration values. So for this we have, for instance, we're saying that the data directory, we get it into a path, we change it, and we verify first if there is the path even, like is there a folder there or not. So if we don't find that, then we raise an error, and it's no directory error. So we say no directory was found. And otherwise, also in general, then we continue, and then we say all the extensions that are valid for our case. So we write them here. This error is just it makes it easier to when you are trying to to fix all the bugs or to have like to the errors that come sometimes. So it's just good to have this. And then we have two lists, and these lists have the valid files and the invalid files. So it's a list of paths. So we have the different paths of the images. And then this is what we have initialized the class with. Then we have the different methods. So we have the validate image, we have a scan directory, and we have delete invalid files. So let's start with a scan directory. So a scan directory does something and does it really well. It's just a scan through the directory, and it returns a list with the valid files and the ones that are invalid. So how it works? So you have the invalid and invalid files. You just clear that out, and then you have a for loop where you are recursively iterating through this directory, and you are this directory that is defined, that is an input of the whole class. And what we do is if the file is present, then we're gonna say, is the file valid, right? So if the file is valid, we are verifying here. We are using a method that will validate the image. And we will talk about the method later, but the important thing is that we are actually checking if the file is valid or not. If it's valid, then we append it to the list. Otherwise, we append it to the invalid list. And that's it. We are complete with this scan directory, right? But that's not all. We have other methods here. So let's go to the validate, which is the one being called here. So validate image receives the image path and returns a bool. The first thing we do is to lowercase the data. So that will facilitate to check the extensions. And if it's not present in our valid extension list, we're just gonna return that it's not a valid file, so it's false. Then what we do is something fairly nice that has TensorFlow is to try to read a file. So try to read it. And for this, that's why we imported TensorFlow here. So we do use this function, which tries to read the file, and then this is for the single image, tries to decode this image. So if in the decode there is an error, it will jump here to this and will tell us, hey, this is corrupt. There is an error. Will tell us the error. Otherwise, if it's, let's say we have no error so far, so we are good. We anyways still check whether the image is still has the form we want, because we have defined this before. So we have the image height, width, and the channels. So we are verifying this, and the same here. We're verifying the amount of channels. So then, if all this is valid, then we say, okay, it's a valid file, so we can use it to train. Finally, you can decide what you want to do with the images. So in this case, I decided I want to delete them. All the invalid ones, I don't want them. So what I did was here, delete invalid files. So it will take, it will output an integer, which is how many files it has removed. So it's this very simple method that basically has the invalid file list that we have defined, and it starts counting in 0 because it hasn't deleted yet. Then if the invalid count is equal to 0, then there is no file to be removed. So we say no invalid file to remove. And we return 0, right? Else, we check all the lists of invalid files. And what we do is to try to delete them with the link. So we are checking this list for all these files, and we're checking on link. So we're using this method to remove the file, and then we print. So be mindful, we use this F to be able to output this file. So we print, file remove, and then we count more the times we do it, right? Otherwise, if something goes wrong, then we're gonna print the respective error. So finally, we return the removed count, and that's it. We have a delete invalid file. As you can see, it is just receiving the invalid files, but it is not directly connected to this, because there is gonna be one code that will run everything. So we don't have to. We're just creating the main functionalities of our code. So don't worry if you don't maybe see the connection right now, but there will be a connection to all of this. So for the time being, we're just trying to do independent live functions. So data processing, this only takes a directory and checks if it's valid for if it has valid files for TensorFlow. If it doesn't, then it will just delete them. But we could do something different. We could move them. We could move them to another folder. So this is an interesting task that you could do. Try to, instead of having this delete invalid files, you could create a method that moves these invalid files to later be processed for us to see, okay, maybe this is I have to change this, because here we are having a data set that is like, we have it for free, it's just available, you can download it, you can it's easy access. But when you are the one providing the data, maybe you want to check, hey, what's going on with the files? Maybe can I fix something? What was the problem, right? So okay, so now we are looking at our dataset manager. So far we have managed the config information, then the config communication between the file we have written to the Python methods, and then we have the data processing, so where we check whether the data that we're getting is even valid for us to use, and then we have the dataset manager. So this we start the code as always, where we specify where is this file located, and then we have the different configurations that we'll import. So in this case, we have significantly more configuration that we're importing, and if you see here, it's all defined. So we're importing the train directory, image size, the batch size, base learning, and all this information. Then we're importing TensorFlow, and we are importing a pathlift. So we have a class that is named dataset. And we have also that this class has, and I probably should change this to another name just to make less confusing. So anyways, the dataset, then we have this initiation, which have all the different information available for the instance. So once we go to this data set, we have only one function. What we are saying is we are returning a data set of images and labels for training and validation, right? So here it shouldn't be the set of images, actually, and labels. Okay. So when it comes to the training, we have only two data sets, as you know. We have testing and training. We in this part of the course, the one available here on YouTube or /Udemy as well. We are not going to work on the testing part because otherwise it would be just too long to have everything just in one place, right? I will leave this for the continuation of this course. Then we have the training. So the training is the one that we're going to use to train. And then we have the two files. So we have the training. We have first the data set and what it outputs. And this is the type of information that will output. It's a data set. And this utility here, what it does is to create an image data set literally from the directory. So that's why we have, if you see, you have tests and you have, training, and then you have different categories, and you have in each category the files. So that way is very easy to create the data set if you have such files organized in this manner. Then we have the train, the train, and we have the validation set. So the training set is the one that we're gonna use to work on the training of the neural network, and this is the one that we're going to use to validate. So we just define first the directory, then you have the validation split that we're passing because available here from this class. We have the subset. This will be the training. We have defining. We have the seed. We have the image size that we are taking from the image size here from this variable. So we're defining here the image size, and we are defining also this information. And we're saying that we want RGB mode. We're gonna shuffle this. We're gonna set true, and we repeat. And we do something similar for the validation set. And this will be basically all. So we're taking all this information, and then what we do is to find the number of classes. So we are giving the number of classes. We have the length, which is the training directory. If we check the length of this and we use that class name, we will be able to know how many classes we have, and we can print this. So for printing, we can add this F here to be able to introduce the number of classes. So we have it found and number of classes, so we can print the variable. And similarly here to print the classes that we have found. So this function will do everything for us in this sense, and that's why it's very nice, very concise. Then we do some optimization when it comes to cache, and just to be able to have to select a buffer size that does it, let's say auto tune. So this is more optimization than actually the data set on its own. But here we have the data set defined. And something that I notice here is that we are returning this, as you see here. We are returning the train validation set and even number of classes as well, which might not be necessary. Then this is the data set manager. You see, we're like literally dividing building blocks our problem. So we have come from the config to the config, from the config text to the config to data processing, now to the data set creation. So we are now creating data set because we have checked the folder and we said, okay, this folder has not invalid files. So now we have created the data set. So now we come to the model. So this is one of the most exciting parts. So we have here the same way we start our files. We have the model. We have the information of the location of this file, and then we have the things that were important. So in this case, actually, if you look around here, I don't use this PLT. So it says here. So I removed it. I'm not using it. So I'm gonna save. And then we're gonna define a class, which is gonna be the convolutional neural network model. So in the first week of the course, we explained like the convolutional part. The convolutional neural network is very useful for classification and is the one we use the most in computer vision models. So just a general description just a general description that I didn't even put here, but this is the data set. Actually, let me just put it. Data set create. manager, class retriever. Okay. Yeah, this is it basically. So I save, and then I go to model. So in model, I have variables that I want to make available for the whole different instances. And here I have the one important aspect that is the augmentation layer. Then we have different functions here. So we have the building model, we have the training, and then we have the save model. So we will build the model, we will train the model, and we will save the model. Okay. So to build the model, we will receive the number of classes and we will output a sequential. So a sequential contains all the different layers that we will define our model. So we say the base model, since we are using also transfer learning, and we already highlighted the benefits of this, is we are using MobileNet. So we're using MobileNet B2, and we are from the Keras application, and we are importing the ImageNet, and we are leaving this important, the top part of the neural net. So we are gonna use our own classification layer, but we're gonna let all the part regarding the feature extraction available. Then we define the input shape, that this is now new because you have the image size, which has the width and the height and the number of channels. And then we have the, this is also essential, that we are not gonna, the base model is not trainable, should be equal to false. Then we define the model itself. So we say model is equal to this. And we open first the sequential, and then we have the layers. So this layer allows to rescale the image. So we rescale to a given size, a given form. So we are doing this. And then we are also rescaling with this from 0 to 1 in order to make it easier for the neural network training. Because as you know, we have the brightness from 0 to 255. But we want to work with 0 to 1 when we are training. Then we have the data augmentation, which is this one here that you see. And then we have the base models on its own, that is this one here. And then we global average pooling. Then we proceed to a dense layer. In this case, I'm using 512 neurons, and we have an activation, in this case, reload. Then we have a dropout, 40%. So we have that at some point we're just gonna randomly drop out, literally, the weights of these neural nets. So this will help us to have a more, in general, less overfitting. So we will avoid this overfitting where we have our neural network is just learning too well the given data, so it's not very good at generalizing. So this is a problem when you're training, because you want your neural network to be as general as possible. So when you put this neural net in another scenario, perhaps different kind of photos, angles, still can predict properly the value, right? So these help us to do that. They help us to just be to avoid overfitting. And then we just have the layer dense. So this is our final number of classes that we have defined before. And with this, we can then return the model for use. So we have defined the model. We have built the model. Now, how do we train this model? So now we're creating a function that is just taking... So now we're creating this method that we are taking this cell, we're taking the training data set, the validation data set, and the model. And you might wonder, wait, how am I taking the training data set and the validation data set? Where is it, right? So the truth is not here. And if you think in general here, we don't have it available yet. There is no training data set available, and you will understand just a bit later why. In all, the why, let me tell you right now, because I don't want to leave you there waiting, is that we are creating a pipeline later, and this pipeline will orchestrate everything that happens with all these different files, these objects, these classes, these methods will be all orchestrated with one file. So this is why you don't have to worry if we can pass information along the different objects without any problem using this pipeline. So with that said, we can then proceed with training. So in training, what we expect is to know where is the training data set, what is the validation set, the model itself, right? And we want to give back the history. So what we're doing is training the model and return the history of the model. I should take out this. No, actually not, because I have it right there. So this is information regarding the model compile. So we are using an optimizer. This one is just a standard. Then we have the loss function. We're computing that, and we have the metrics. So this is the compilation of the model. Then we can define an early stopping point. This value you can put 5, 3. Just don't put a very high value at first, because you don't know if it's going to even converge the model or anything. So then you are what you're monitoring. So in the case, we're monitoring the validation loss, and we're going to print if we have an early stop, and we're going to try to restore the best weights we had. So this is a function of Keras. So you see early TensorFlow Keras callbacks, early stopping. And then we have the history. So in this case, we have the history that we're defining, and is the training data set, the validation data set, the epochs, and then the callbacks. So with this, we have defined the history, and then we can return the history. So this is how the training proceeds. Basically, we are taking the training data set, we're taking the validation data set, and we're taking the model, and we are compiling this model, and we are giving back the training of the process. Then finally, another function that we have here is the save model. In this case, we just take the model and we just save the model. I'm going to use TensorFlow Lite, and this is because the idea or the vision of this of the full, let's say, the full extent of the workshop is then later to integrate this into edge device or something of that nature, and then we're gonna then convert to TensorFlow Lite. So the first thing we do is to create to check whether we have in the model directory that we have defined, which is this one, models. If first of all it's true, like does it exist? If not, then we gonna create this folder. Then we see the model file path. So the model file path would be for instance, the naming we want to put. So in this case, classifier. And then we proceed to do the conversion. So we're using this functionality to convert the model. And here we convert, right? Then what we do is to write, that is to save the file onto the folder. So you see here there is the model, and we have something, we cannot open it, but we have the classifier information. This is the save model, and you can see is not receiving anything more than the model on its own, and the rest is just It's not even connected to the training, as you can see. It's not even connected to the build model, because at the end of the day, we will orchestrate this with the pipeline. Okay, so now we have to create another file, and this is the almost the last one we have to create, and it's the pipeline. And as its name indicates, it is where we are gonna orchestrate sort of the whole processing, training, and evaluation of the model. So we're gonna go through each part of this code together, and we're gonna start by defining. So just gonna start by defining what we're gonna import, and I just want to remove some of the stuff that I'm not using. And so we're gonna import matplotlib. Make sure you have installed the matplotlib under the environment. But yeah, if you've followed the tutorial, you have done that already. So then we have from the data. Now we're gonna use all the files, right? All the files we have created before. So here we have data processing. From data processing, it says I'm importing the image processor. So I'm importing this class. Okay, great. And similarly, I do the same for model and for dataset manager. So from dataset manager, we have, sorry, I made this dataset and dataset small, but we have the class. So we're importing the class in this case, you see. And then we are importing all the different configuration. Import the model directory, the training directory, and the testing directory. Okay. So what we do is to create then the class, which is the classification pipeline, and we initiate some of the values. For instance, image processor. Remember the image processor, if we go here, takes an input. So we are providing that input, right? Then we are using, we're calling the model that we've created, the convolutional neural net. And finally, we're calling the dataset, right? Then I'm putting here also the model directory available to the instances. And we have also these variables that we have initiated as none. Then we proceed. So the first thing we want to do, of course, now we have to think of the same logic, the same workflow that we had, that we were saying, okay, let's think first of the image. We want to make sure that all the files within for my neural network are valid files, are how I want these files to be, right? Otherwise, it will crash anyway. So, but then we start with a workflow like that. So we are saying, okay, process image self. So we are saying we're gonna scan the directory, and we're gonna say scan directory, delete invalid files. So since we have already given this image processor, we already given the train directory as input. So we're here scanning this directory. Then something that I might explain here because it's easier. You might see this that might be a bit confusing because you see self image processor, you see it here, and then you see this scan directory here. Let's trace back where this is coming from, so it is less confusing. So scan directory, let's trace it back. Scan directory is traced back to self image processor, which is here, which is traced back to image processor, which is traced back to data processing. You see? So if I go back to data processing, then we have that there is a method that is a scan directory. So let's go back to the pipeline. So scan directory, we are in the data processing, we scan directory, the class image processor, and that's it. We're importing. So we are accessing this. So that's why you see all these points. Nothing more. So the same logic will apply for all the different methods that we will use access here along this pipeline. So this is the first one. We just check in the files, we're deleting. I hope you had the time to try the moving instead of deleting. Would be nice, as I was playing before. So that would be one interesting to do. Then we have the training part. So in the training, we have this part, which is we have the dataset builder. We're building first the dataset. So for this, I'm using self dataset builder, right? And I'm accessing the dataset method, which might be confusing because you're accessing is it's here. We're accessing this dataset method. And if you see this dataset method is returning three variables. So what we're doing is accessing those variables here. That's why you see this variable here. And now we proceed with the logic. So now we build the model. So for this, we're giving the number of classes. Because if we go back to the model, we see that in order to build the model, we need to use, for instance, the last ledger needs to be the number of classes we want to classify. So then we need to know. So here is given to that. Then similarly to the history, and similarly to save the model, which is another method we saw. Finally, we can print where we save the model. We can proceed and say that the training is completed. And there is another one that is essential because it allows us to evaluate the results, is the plot. So in this case, we have the plot results, and we have none. We are first trying to see if there is this history of the model. So we have all the information of the training set, validation set, and the model. If there is not, then we can say, okay, it hasn't been trained yet. Otherwise, we proceed to give the plotting results. So here we have a fairly simple graph where we have the history accuracy, we have the validation accuracy, the loss, and the validation loss. We have graphic. We are using the graphic as basically the number of epochs we have, and then we have the one for accuracy and one for loss. So these are two independent figures that we have here. Here one, here the other one. And that will be all, basically. That will be all regarding our pipeline. You see, the pipeline allows us to just simplify things and just encapsulate sort of the functions that might be more complex, such as this one, for instance, these two. Maybe reuse it. So congrats for making it this far. We're almost at the end of our process to create, and we will close it with something that is the main Python file. So this is the one that we are actually gonna call for, let's say, or we're gonna run. And this is again another we start our file as usual, and then we're importing this one. So this importing allows us to get all the different commands, and it will be the entry point to getting all the different arguments from the user. Then we are importing also the classification pipeline here. And then we have the argument. So we have the possibility of running different processes. So we have the preprocess, which is the data. And we have the data validation and deletion in this case, or if you have modified the method as I suggested, you have moving instead of delete. And then we have the training, and here we basically define, right, what is going to be the situation. Then we add the arguments. So so in this case, we are saying what the choices the user have, and something important that we can add is the type. So it could be actually comparable, because the person might write just in lowercase, uppercase, so it's best just to have it robust. So you have pre-process or train. That's it. Then we have the help. So help the process to run by selecting pre-process train. Okay. And with this, we have the arguments. Okay. So we have the argument set up, and now it comes to the classification pipeline. Since we have defined the pipeline, it's available within this method. What it says is just if the argument that we have is pre-processed, then it will run this pipeline, pre-process images. Otherwise, we'll run this pipeline. So you can see you can use elif to just add more if you have a pipeline that it has significantly more functions. And you can add different options here. So you can say comma, and then you have another one, and so forth. This will be the main Python file, and this is the one we're going to run. And here we have officially finished sort of this beginner-friendly, this neural net. So now when it comes to executing our code, we have here in Visual Studio Code, we have all the code. When it comes to, let me just delete all of this. So we have our code here, and we're going to run it through the main Python file. And for this, what we need to do is to, firstly, to navigate through to this file. So now I'm located in the file, and then I can just go to be aware that you need to activate your environment. In this case, I have the testing environment, which I could run it from, but I already have a specific environment, which is object recycling environment. Oops, made a mistake there. Conda activate. Clean environment. Oh, it is actually activated. Okay. Anyways, so we can then run the file. So I'm just gonna type like that just to show you Python main.py. To saying like main.py error. The following arguments are required. So we have to specify a process. And then we says here, okay, we have pre-process or train. So I'm going to run then main Python main.py, and then I'm going to say pre-process. Just to try, I'm going to do it like this, pre-process, just to see. So you saw it just took, that's why it was important to have this lowercase. So it just is more robust. And in this case, there is no invalid file to remove. But I'm pretty sure once you download the data set, you will find a files to remove. The things are already removed then, so they're not available anymore. Then we set the other part. So the training. So in this case, it's working, and it said that it found 974 files belonging to 4 classes, and is using 780 files for training. And when it comes to validation, it's using 194 for validation. And here what we have is also that we use a regularization technique. So these regularization techniques avoid overfitting. So it means that if you have a very high accuracy on the training data, but then when it comes to new data, the neural network performs poorly, it means that you're just overfitting. So hello and welcome back. Today we're going to explore our results. The first thing we're going to do is to check what we have obtained from the previous training. For this, I have a plot with me that I want to share so we can study it together and find points of improvement. So here I'm opening the training and validation loss. So here what you see is that we have training loss on red, and we have the blue, there is a validation loss. Then let me open also the accuracy, so we can have both side to side and see what's happening here. So from one side, we have the validation accuracy, and you can see probably that there is this gap. So we have this gap in between the training and validation accuracy. On one hand, we have that the validation accuracy reaches around 80% of in terms of accuracy, whereas the training accuracy remains low, as low as 35% on average. So it indicates that our model is performing well with the new data, but also indicates that the training is not being performed in a good manner. That is, we're not allowing the neural network to learn enough of the data. So also we see how stagnant it is the accuracy. So this occurs because we have used regularization techniques. So these regularization techniques, they imply that we have a more difficult training time. So for instance, we are using data augmentation. When it comes to data augmentation, we have the data on its own is randomized. So we have something that is more bright, it rotates. So it makes difficult the training, right? On the other hand, we have that we are dropping some elements, some weights when we are also training. So this together combines to have these results. So these results are not good. We want to have ideally curves that are relatively close, and also if we can, we should have better accuracy. Similarly, the validation loss, we have different. Thankfully, both go downward, but still we have this issue, right? So how do we solve it? I think we have to first try to be less hardcore when it comes to the data augmentation. So how can we do that, you might ask? For this, I have here the model, and I will show you which changes you can perform so your neural network will be in a better place. So when it comes to data augmentation, we have here, so I have reduced the number, as you see here, to 0.1. And here I have also eliminated these random variations. It means that we have less data variability when we are training. We still have this data augmentation because it helps us to avoid overfitting. On the other hand, we have the built-in model. The built-in model we have here has the data augmentation, as you know, and then we have the layers. I have added another layer. So we have 2000 elements on the first one, and we have 1000 on the second one. Then we have the regular classification. So in this case, as you can see, I have taken out dropout, and this mainly for the reason that we already have the data augmentation. So you see what happens. So let's run this code and let's analyze together what happens. Before running the code though, we need to verify that we have the same configuration. So in this case, I'm going towards the image size of 224 times 224. Similarly, the input shape becomes that. And then we have this batch size of 64 and this relatively small learning rate. And we have the numbers epochs. In this case, is 70. So this is with the given categories that I've chosen, which is cardboard, plastic, paper, and e-waste. This is a good compromise I found. So we can start the training and see the results. So here we have the results now. As you can see, we have the training and validation accuracy, and we have the training and validation loss. From one side, we have the validation accuracy. In this case, we have the training and validation are fairly close to each other. The validation accuracy is slightly on top. And we have similarly the loss function. So in this case, we are even reaching a higher accuracy. So we are reaching around 86% in validation accuracy. And our model is, as you can see, has a good fit with the data and the validation data. As a result, we have improved our accuracy, and if you notice, we have here 70 epochs, whereas with the other one, we had, let me just open this plot for you. We have even 200. So you can see that we are in a better place. We are being more efficient, and we are obtaining better results, very fit, and with less iterations. So this is good. This is a good change. We have accomplished some decent results, and now we can move on to the next stage. So the next stage is to use the testing data and evaluate whether this is accurate, whether what we have here is truthful, at least with the testing data. Then in the next part of the course, in the workshop, we will work on evaluating this with real live data, and it will be really fun for sure. But for the time being, what we will do is to test with some information, and I will show you how to do this part. So if you remember, we have data and we have here test and training. So you know that the training, these are the ones that I use for training, so only 4 categories. And here we have the testing. So these are different images. So what we can do is to test whether our model is performing well or not. From here, what we can do, we can introduce something in our pipeline to help us classify. For this, I have imported this module, which is a pillow, and NumPy. So this is to process the image that we want to infer. Then we have, as you can see, we have some path that we are importing here: test directory, test directory, test directory, and test directory. These we need to trace it back to config and to the config document. So in the config document, we have that I have specified the location of these testing directories. After that, we can move on to the config file, and we can see that the testing directory plastic, paper, e-waste, and we get this data ready for the pipeline. Now we have imported this, and we need to create another method. In this case, I call it Inference, and what we have is that we take the specific directory and we scan this directory, we delete the invalid files, and then we load the model path, as you see here. We take the class names and we open this document that contains the class names of the model we train. And you might wonder where this class name came from. So again, we have to modify the model in order to add this possibility, because we do have the classes. The only thing is we need to save this as a document, as you see here. So how do we do that? We can do that by coming to the pipeline and to the training. So here in the training, if you see, we have added this part. So this part is fairly simple. What we are doing is taking the class name and creating a path where we have the class names along with the model. So we are saving all of this together. Then we do a try. So we try to open this document, right? And what we do is to put the information, the class name, which is an output of the neural network, of the training, sorry. We have then that we print that we have saved this. Otherwise, we output an error that we couldn't save that. So you see, it's pretty easy to add these, to save these classes, because is information already available during the training phase. Then, so we can come back to the inference method. So we were here, right? So now what we do in this part is just to try to open that class file, the file with the class names. And from here, we create one list with all prediction, and we also create a dictionary where we have the percentage of each class and the value. What it means is that we're going to have the result. We're going to have, so for cardboard, 78% was correct, or 20% for each of the 4 categories I have. So now what we do is we try to preset to, this is the thing that we're going to do. So here, for instance, we are iterating on the valid files because we have performed a scan before. And what we try is to open the specific path, and we convert that file to RGB just to be sure we don't have any issues. Finally, we resize the image to the specific input of our model, which we could see here because we have specified this before. So we then proceed to convert this image and to create a batch of a single image from here. Finally, we start with the predictions. So these predictions is using the model. So this model. And this model that we loaded here, we are using the method predict. And what we're going to predict this image batch. So once we use the predict method, we have the index and the text. So with this, we can save all this predicted text into the old prediction list that we have created. After that, we can use this data for the final prediction, for the final output. So now we added to the list all the predictions we developed or we executed. If something happens along the way, we're gonna print an error, and then we're gonna try to relate the different categories. So from here, what I'm doing is to evaluate and update, basically, because we have a dictionary with that will have the class name, the specific class name. We have all the predictions, and we'll count the ones that belong to that class name. And then we're gonna divide everything for all the predictions and the 100% and 100 just to give the percentage. So this will be the way we're gonna obtain the percentage of each class. Finally, we also put an error in case, and we return the percentage each class. That is the dictionary. So if I run this, I will show you an example. Here we have one of the examples. So for these, I have placed inference in the Python main. I added a new method. So this is fairly easy to do because we can go to the main Python file and add another one here in the choices. So we add inference. Then we can add another elif and just add this time we're going for the inference. So this method. Like that, we will have this process. So this process is showcasing that when we are training for e-waste, in this case, we have that the cardboard is fairly low. We have some confusion with paper and plastic, but around 89% of the time is correct. And we can do the same for all the paper and the cardboard. While the results are not as high as e-waste, you might understand as well that paper and cardboard are sometimes a bit difficult to distinguish. So our neural network might struggle a bit more there, but still we have results far over 70% in those scenarios. So you can see that this inference method, we are taking test directory and we are taking this test directory and I'm writing each of these directories that I want to test. Ideally, you want to do this automatically. So that's your homework, basically. Try to create or to improve this inference in such a way that we can have, just by typing inference in this terminal, we can have the results for all the different classes. So I don't have to update this because what I do, for instance, let me show you. If I'm going to go for plastic, you see that I place plastic, I save, and then I come back here and then I type inference. So you can see in this case, we go plastic 85%, and we have some other some mistakes basically, because the whole directory is plastic. So in theory, it shouldn't have said that there was cardboard or e-waste or paper. But we know, of course, with the training that we don't have 100% accuracy, right? So we do make mistakes. And you see, it's fairly manual, this inference function. So it needs to be improved. It needs to be automatic in the sense that we have the different categories and we're gonna just press inference and all the different categories are gonna be output. So that's something that you can do. You can add to this, and you can maybe share with the rest of us how you did this change, and looking forward to see results.